In this video, we are going to discuss linear and angular speed to describe motion on a circular path. Okay, so the first thing we're going to deal with is linear speed. So let's first talk about what's actually happening. So we take a circle, and what we're looking for is we're actually just trying to figure out how fast we're moving along that straight line that I just drew through here, right? From moving from one point to the other, I want to know the speed linearly, like how fast is it going? How we can do that is we take our S, remember S is arc length, that is the length of my red line that I drew, and I divide it by the time that it takes me to get across there. That gives me a speed. The reason we call it speed here, not velocity, is because we'll just assume that our arc length is positive. Time's always positive as well, so we don't have a velocity, but we have a speed because we're ignoring the sign. So that's one thing that we could describe, figure out if something's traveling on a circular path, how fast it's going. We also care about how fast the angle is changing. So what I mean is what we would measure is if we start at this point and we moved over, we would want to know how fast is theta changing inside there. So how we do that, this is called our angular speed, and this is, if you need help with that Greek letter, it's omega. Omega is equal to theta. Theta is how much of our angle changes over the time it takes, which gives me a rate. Just like take distance and divide it by time, you get a rate. We take how much it changes in theta, and we get a rate. All right, so this leads us to some other equations. I'm going to just talk through it pretty quick, and then we'll use the formula at the end. So if I start here, S equals R theta, and I also use the this formula here for omega. So if I solve for theta, I would multiply both sides by t, so I'd get omega t equals theta. That's just manipulating multiplying by t, right? Multiply by t, and I get that formula. So what they did is they took their theta here in that formula and replaced it with omega t. So now we have that S equals R omega t. And then now we go back to our velocity or speed formula. Speed is arc length over t. And when we replace our S with the R omega t, the t's cancel, leaving me with this formula. Speed is equal to R times omega. All right, so we're going to use that formula, do a few problems now. An old vinyl record is played on a turntable, rotating clockwise at a rate of 45 rotations per minute. And now that's going clockwise. We're going to ignore if it's clockwise, it means it would be negative. But since we're talking speed, I don't really want to change this. Speed's always positive. Velocity is the one that gets us negatives, but speed isn't always positive. Think about your car. If you're driving and somebody asked how fast you were going, you would never say negative something. It'd always be positive, no matter which direction you were going. So we're going to do, it says rotations. I'm going to call them revolutions, just so I can do that, per 1 minute. And what we're going to do is we're going to make things cancel. This is called dimensional analysis. I have it there on the screen. I have used this through physics, through a lot of my classes. You may have seen it before, but the idea is multiplying by factors of 1. So what I mean here is if I multiply this first one, I want to try to convert minutes to seconds because they said that, right? Radians per second is our goal. We want to find the angular speed, omega, in radians per second. So I already have omega because they gave me a rate here of how fast it's rotating. That is omega. So I wrote 45 revolutions over 1 minute. But now I want to cancel. I want minutes to go away. So I'm going to put a minute up here, or minutes. And then I'm going to put seconds down here. And we are going to write a 1, right? We want a 1 inside of that. So it's going to be 60 seconds is 1 minute. So why I'm doing this is because when I multiply by 1, nothing changes, right? Take any number, multiply it by 1, you get the same number. This one's going to look different, and it's going to make my number look different. But the whole point is we want it to be equivalent when we're done, and that's what happens when I multiply by 1. And why this method, why I like it, is it tells me what to do, like actual multiplication or division. I don't have to think about it. I just have to put it in there, make sure the minutes cancel. All right, so right now I have revolutions per second. That's what would be left. We don't want revolutions. We want radians per second. So if I want to cancel that revolution, I'm going to put the revolution on bottom since that one's on top. And then I'm going to put radians over here on top. So the revolutions are going to cancel. See the rev here, that rev. but I need this to be a 1, so it would need to be 2 pi over 1 revolution, because that's what is equivalent. Notice that if I do that, 2 pi radians over 1 revolution is a 1, so when I multiply, nothing actually happens. Why I like this is now, look, the units made sense. There's radians on top, seconds on bottom. I didn't really have to think about, do I multiply or divide? All I had to make sure of is to make my units cancel. So I multiply straight across. I get 90 pi over 60 is our new rate, and this is radians per second. We could even do 3 pi over 2, and we get radians per second. So that's how we do that. This dimensional analysis has helped me out quite a bit. I think there was a physics 1 test I had where I had to figure out how much it would cost to concrete a portion of a highway, and this dimensional analysis was how to go about it. It made it very, very simple. There were like 10 of these, like different, like to convert, which is really great because you don't have to think about multiplying or dividing. Okay, I got one more problem. If you need to pause and take a picture or draw this out, that's fine. I just wanted to save some video time because I know these can be a little bit much. So a satellite is rotating around the Earth. We'll go ahead and assume the Earth is round. It's a little oblong because of gravity, or the rotation, I guess, rather. It is rotating the satellite at 0.25 radians per hour at an altitude of 242 kilometers above Earth. If the radius of the Earth is 6,378 kilometers, find the linear speed of the satellite in kilometers per hour. Okay, so a couple things I want to point out. I drew my picture here. They gave me the speed. I guess I could write that. W, or omega, sorry, is 0.25 radians per hour. And the reason I know that is because it's an angle unit, right? Radians per hour, it's not a linear speed. It's not V because it's not kilometers or anything like that. Another thing that's kind of tricky, it's tempting just to use this when we're trying to find the linear speed of the satellite, but the actual radius of the satellite is all the way across here, right? It's going to be that sum there. So this is going to end up being 6. Actually, I probably should do this 0, 12, carrier 1, I got 6, there we go. So I know that, and if that's slightly off, forgive me, I just did it in my head, but that's the actual radius of the satellite. Okay, so couple things. This is my velocity, that's the thing we're looking for, right? We could figure out right here, oops, I thought I was on a highlighter, but I'm on a pencil. This is the formula for velocity, or speed, I mean. But in this case, what I would have to do, I don't have an arc length, right? So I would have to like figure out an arc length and then figure out a time. Now I could like work backwards from here, right? I could plug that, use the formula and work, or the formula that we came up with was V equals R omega, and I could just plug these in. The R is 6620, the omega is 0.25. Okay, and then if I multiply that, let me grab my calculator real quick on my phone. That is going to be 1655, and this is going to end up being kilometers per hour. That's just using the formula that they gave us. These can be a pretty big, can be confusing at times, and typically the mistakes that are made are stuff like this, right? Just forgetting that the radius is a little bigger. And then one thing that they may do also that you need to pay attention is we need to make sure that these units line up, right? That kilometers and kilometers. They may give you one in miles and one in kilometers. That'd be very annoying, but they may do it. So be aware.